Let's turn to Chapter 4, which is on the Laplace transform. So this will provide a method in which we can find our system output a little more simply than using convolution in most cases for most inputs and for most systems. We'll start with coverage of the introductory section and define the Laplace transform. We're going to use what's known as the unilateral transform. Unilateral Laplace transform. So I'll be abbreviating this quite often as just LT. And a little bit on the notation here, we typically use a capital X to represent the transformed function. It will be a function of our complex frequency variable S. And in the unilateral transform, our integration is from 0 minus to infinity. Most times the distinction between 0 minus and 0 plus won't come into play. For any function that's continuous at the origin, it won't matter, or even if there's a discontinuity, it only comes into play if our function involves an impulse located at the origin. And it's an integral over the product of our time domain function and e to the minus st, and we integrate over all time. So the time variable will disappear, and our Laplace transform is just a function of s. Again, the way we're defining it, we'll only be solving systems we'll only be finding solutions for the time interval t greater than 0. There is a bilateral Laplace transform that can also be used where the transform is defined over all time. The corresponding inverse Laplace transform can be found. We have to integrate over s now. It's 1 over 2 pi j, and so since s is a complex variable, we actually have to integrate over a contour along any real line from c minus j infinity to c plus j infinity of our x of s function, e of st. You typically don't learn about contour integration though until you've taken a course in complex variable theory, so we will not be using this formula to calculate the inverse Laplace transform. Instead, we'll be using a table lookup to find the inverse transforms. This is fairly common and simplifies the work considerably. Little bit of a few notes on or comments on notation. So I've already introduced capital X of S as the Laplace transform. Sometimes we'll see this written as that's a script L or cursive L. So this is another way to indicate the Laplace transform of a time domain function x of t. You can write the inverse transform as L to the minus 1 to represent the inverse. It's not a reciprocal, but represents an inverse function. And then you may also see the notation with a double-sided arrow indicating that we can go from the time domain into the S domain, the complex frequency domain. So this would indicate that x of t and x of s are a complex conjugate pair. We will work with the Laplace transform by first constructing a table of common Laplace transforms. It will be a fairly short table, but by using various properties of the Laplace transform, we can extend it to work with a much larger range of functions, much like what we did with the convolution table. So to construct the table, we want to find the Laplace transforms of some common engineering signals, and we'll use the defining integral here to find these Laplace transforms. And it's the integral of the product of our function. Here we'll first find the Laplace transform of an exponential, a switched exponential, times e to the minus st dt. U of t is 1 everywhere within this interval, and I can combine these two exponents and write it as e to the minus s minus lambda t dt, and integrating that, I'll get minus 1 over s minus lambda e to the minus s minus lambda t, evaluating at 0 minus and infinity. At t equal infinity, as long as this difference has a positive real part, this term will go to 0, and when I evaluate this at 0, I get 1, so I'll have 0 minus 1 or minus 1. So the final result is this quantity times a negative 1. And so the resulting Laplace transform is of our exponential function is 1 over s minus lambda, and then the restriction for this term to go to 0 is this is valid as long as the real part of s is greater than the real part of lambda. This term will go to 0 when we evaluate it at t equal infinity. In a similar manner, we can find some other transforms by just a direct evaluation of the integral. And the Laplace transform of the unit step is just a special case of the previous problem. We just evaluate this with lambda equal to 0, and we immediately get 1 over s. Similarly, we can find the transform of e to the j omega t u of t, again from our more general e to the lambda t, just plugging in j omega for lambda. And so this is the Laplace transform of our complex exponential. Find the Laplace transform of cosine omega t by applying Euler's formula and writing cosine omega t as 1/2 e to the j omega t plus e to the minus j omega t. And so that's going to be equal to 1/2, and then we'll have the 1 over s minus j omega. That's the Laplace transform of the e to the j omega t, and then I'll also have 1/2 1 over s plus j omega. Here I'm making an assumption that the Laplace transform is linear, so that the Laplace transform of a sum of time functions is the corresponding a sum of the individual Laplace transforms. Haven't really proven that yet, but the Laplace transform is this integral operator, and integration is linear. I can actually simplify this result a little bit by putting the 2 over a common denominator. That common denominator would be s minus j omega times s plus j omega, and then here I would have the s plus j omega term in the numerator here, plus the s minus j omega here, and the j omegas in the numerator cancel. I'll have a 2s. The 2 is canceled by the 1/2 in front, and so I'm left with just an s in the numerator. And if I multiply these out, the denominator, I'll get an s squared. I'll get a minus j omega s and a plus j omega s term. They'll cancel, and I have a minus j omega times a plus j omega. Minus j times the plus j will give me a plus 1, and then so this simplifies fairly nicely into just s squared plus omega squared as the Laplace transform for cosine omega t. So similarly, we could find fairly easily find the Laplace transform of sine omega t in your textbook, and I will also provide a copy of this in a handout, table 4.1. It's on page 344. List several other common transforms, and in the homework assignment for today, you'll be finding some additional Laplace transforms, actually by direct evaluation of the integral. But then as we get farther along, we'll be using almost, and learn more about the properties of the Laplace transform, we'll be using almost exclusively the table to find our Laplace transforms and also find our inverse Laplace transforms.